Okay, I wanted to just give you a quick rundown on electrical power systems. Unfortunately, we lost some of the presentation last night, so I just want to give another quick run through this in about 35 minutes. There's 130 slides, by the way, so a huge amount of collateral, but we'll go through it very effectively and quickly. The important point to make is that these slides are all available, the recording's available, and I just really wanted to go through the critical stuff in these slides. As I said, there's 130 slides. I love entrepreneurship, resilience, and I love education. So that's basically what I'm about, and that's my background. So today, just a quick summary of the objective. Just talk about generation, transmission, distribution, transformers, earthing, grounding. Obviously, earthing's used in the IEC universe, and the North American IEEE would generally refer to grounding. A few mentions of protection, and then wrap up. So it's just a quick introduction to the topic for your edification. So just quick structure of the power systems. As I said, I'll take about 35, 40 minutes to do this whistle-stop tour through these slides. And it's obviously just providing the basic blocks just to think about. So electrical power distribution, transmission, distribution. Obviously, we just want to focus on the actual generation, and there's basically three, or should we say four forms. Obviously, this is where you produce watts, power, and we want to obviously get that through the transmission lines, distribution lines to your home or factory or whatever. And there are the diagrams have got obviously fuel energy, hydroelectric energy, and nuclear power, plus renewable. So they all play a role today. So the idea is you have a rotary engine, extracts energy from a fluid flow. So you've got the flow going through, and you have blades, rotation, kinetic energy, and that creates connected to electric generator, which provides kinetic energy to electrical energy. So as you know, with kinetic energy, EK half mv squared, and we really want to focus on that. Obviously, if you're looking at a hydroelectric scheme, you've got mgh, potential energy, and the water comes down through the turbine and away you go. Or you could even use a pumped storage system, which is like a gigantic battery to store your energy. One particular installation I had in Cape Town, South Africa, which they used to obviously store the energy in a dam on top of a mountain, and then during the night when no one's using power, they used to pump all the water up to the top of the mountain, and then during the day at peak times, winter particularly, you have the turbines operating because you're running the water down from the dam like a storage battery. And obviously generators are pretty critical. The idea is that you have a metal shaft connected to a turbine, turned by falling water or steam, or indeed gas, burning gas. Turbine rotates, shaft also rotates, and you produce electricity, as we've shown here. Coal-fired, which is obviously not very popular today because of emissions. You burn the fuel, heat the water, make steam, steam turns turbines, turbines turn generator, and you send electric power at high voltage around the country. Turbine power plant. I've worked on a few installations over the years. Caterpillar, Mars turbines. Can be quite expensive using gas turbine, but this turbine power plant, again, natural gas line comes in, combustion chamber, compressor, air intake, turbine, exhaust gases, and you have the generator connected there, the coupling, and of course transformer, and high voltage to transmit to try and reduce the current. Hydroelectric power, again, very similar arrangement. You can use pump storage as a battery, very clean energy, and nuclear power is the other point. Again, fission makes heat, but I notice there's quite a few announcements now on fusion, which may hopefully be the future with nuclear power. Still a way to go there. Heat water to make steam. Steam turns turbines. Turbines turn generators. And again, you distribute the power. So this is the diagram of the modern power station. And of course, you've got alternative renewable solar energy, which is probably photovoltaic cells, geothermal energy, New Zealand, for example, although you can run out, biomass energy, ocean energy, and the other one is, of course, wind energy, which is very popular. Solar energy, photovoltaic cells, and the idea is that you generate electricity and from the sun, very popular. Wind energy, and can be a blot on the landscape. And I suspect, I don't want to take any position here, but I suspect there's going to be a challenge in the future with reprocessing the photovoltaic cells and the wind energy. But the great thing about both of those is that you can be off the grid and you've got a very cost-effective form of power if you're in a remote location. Transmission of power is the next story, and obviously high voltage is very important. Most of the power that we distribute is at alternating current, which looks like this, but obviously DC, high voltage DC can be done now. Electronics is very good at dealing with the taking the voltages up and down. Transformed up to 400 kilovolts, and high voltage minimize losses. Losses generally are I squared R power, because that is your issue that you need to try and drive down as low as possible. So that's why we need high voltage, and means our current to transmit the same amount of power will be low, and you have low level of losses. Transmission towers, very important. Concrete poles, steel towers, occasionally wooden. Wood actually has to be dealt with carefully. You could get leakage of current down the pole and some losses there, but let's not talk about that now. Mainly distribution. Transmission loss, lightning strokes, huge current flow, I squared R losses, and obviously transmission interruptions can be due to tree limbs, and a lot of the issues today are resolved by transmitting the power underground. I've even seen distribution in cities completely move from above the ground to underground, meaning when you've got a winter storm, less issue with interruptions to the power. Distribution of power is the next issue. So you go transmission, and you could be, you could also have 132 kilovolts, which is sub-transmission, but generally quite a lot lower voltages. And typically 33 kilovolts, 22 kV, 11,000 volts, very easy to transmit power. And obviously you have transformers, and that's the next topic we'll spend some time talking about. 132 kV, 33 kV, 11 kV, substations, and obviously industry or towns. So these are quite important. And here's a typical example of a substation. Here's your voltage coming in. Lots of circuit breakers, and then of course the outgoing distribution line. So you've got your sub-transmission line coming in 132 kV, and you're going out at 1122 kV. AC power, this is always a very interesting comparison, and this is something I spend quite a bit of time talking about when I'm teaching the subject. This little triangle, you've got Q, which is VARs, all lowercase these days, watts, and that's in VA, volt amps. So S squared equals P squared plus Q squared. And the important point is if you've got a whole lot of loads, say, for example, let's call this S1, S2. The idea is that you can, if you're trying to size the total power here, you would actually add up the total equals P1 plus P2, and Q total equals Q1 plus Q2, and very importantly, S total, volt amps, is going to be the P total squared plus Q total squared. S total is not S1 plus S2, bear that in mind, mainly because this is your angle, power factor angle, cosine phi is your power factor, and obviously this angle could be different for the different Q1s, P1s. And obviously power factor, as I said, is theta there, S, Q, P. Always very interesting challenge when you're doing calculations there. And typically the big issue is that you've got an angle between your current and voltage. It's the distance between the current and voltage. So there's your voltage, current could be pi, like that. And obviously there's an angle between them. That's your power factor. Obviously the trick is to get the power factor cosine phi equal to 1 if you can. Very hard to. So let's talk about transformers now. So transformers are basically to raise or lower voltages. And I suppose if we didn't have AC, we wouldn't need transformers. And obviously the very famous formula, you've got your primary, secondary, and obviously the voltage in the secondary divided by voltage in the primary is equal to turns in secondary divided by turns in primary. And the power, the primary is volts primary I primary equals volts secondary I secondary. This is not quite true because there's always losses in the core. So large power transformers, distribution boards, and that brings us smoothly on to earthing grounding, which is obviously pretty critical, need for earthing, and there's some diabolical safety issues if you don't focus on earthing for a home. Earthing is absolutely critical, so it's an important thing. If you have your bad earthing set up, you don't connect it up properly. That's why electricians are so absolutely important. They're well trained. If you don't have the earthing set up in a home, you could get the return current going through a tap, and I've seen some horrible injuries to little people, kids, and obviously disaster due to electrocution. So obviously we want to avoid this at all costs. So direct contact shock, indirect shock, and this is basically a tap or something which is because you haven't done the wiring properly. And obviously fixed electric shock depends on the amount of current, path of the current, So if your current path is across your chest, you could have a problem there. And obviously length of time and the frequency of the current. So you can have a small amount of current. So muscular contractions freeze the body. So obviously we want to avoid electric shocks at all times. And what's worse about electric current, if you're touching something, your hands close around what you're touching. So to pull it off is quite hard. So obviously to be avoided. Touch potential and step voltages we often talk about. So touch potential is the voltage between the energized object and the feet of the person, contact with that object. And so here's an example of step potential and touch potential, touching something. So earthing is absolutely critical. And bonding conductors and earth electrodes, two main types of earth conductor. And obviously the idea with earthing is to try and make sure that your earth stakes in the ground are as low impedance as possible. So I won't go into earth electrodes is a very good standard, IEEE 80. Very important field. As someone said to me, AI is unlikely to take over the world of earthing on a site. It's pretty, needs a huge amount of skill to do it properly. You can get vertical rods, plates, and horizontal conductors for earth electrodes. Vertical rod most common, cheap, and low resistivity. Soil is very important, so rock is pretty hard. Then power quality is the next issue, and that is obviously with electronics around, power quality is very important. And you can get different causes of power quality, voltage fluctuations, dips, interruptions, voltage imbalance, power frequency variations, harmonics. Harmonics are, if you look at a typical sinusoidal waveform, you would have something like that, 230 volt AC. But in fact, most of the time it has a bit of a, and basically this means that your harmonics are, if you take any waveform, no matter how horrible it looks like, you can always decompose it into an infinite series of sine waves at different frequencies. And you have the fundamental frequency, the basic one, 50 hertz, and then you have the harmonics, 100 hertz, 150 hertz, etc. And they are called harmonics. So voltage variations, sag, swell, long duration, under voltage, over voltage, important. Voltage sags, like this. Short duration voltage variations. Short duration voltage variations are due to single line to ground faults, equipment over voltages. I won't worry about that too much. Long duration voltage variations. Variation of frequency, we've got to keep it to 50 hertz, very important. These can cause some issues. Most of the time, this 50 hertz is the typical one in Europe and Australia, but 60 hertz in North America. Obviously, keep it as close to that as possible, that frequency. You'll find that if you've got a remote site, a mining site, and you've got a generator there, as the load goes up and the generator can't cope, you may find that the frequency drops to accommodate the inability to match the load with the supply, but very unlikely today. Interruptions, you can get interruptions due to lightning strike, lightning stroke, temporary faults, tree limbs falling across conductors. These are pretty. And the surge is an unexpected increase in voltage, 110%. Surge protectors are quite critical because if you get a surge going through your electrical system, your TE, you'll damage it. Switching surges, lightning surges, probably the worst one. You could have direct flashes, induced overvoltage caused by coupling from other systems. And obviously electronic devices may operate or you may damage them permanently. Lightning arrest is very important, but just bear in mind they don't stop lightning coming down to the side of the building. That's always possible. It's got a lot of misinformation there. Harmonics, when you've got nonlinear loads, you've got electronic equipment, you have switching going on, and you'll find that you don't get a nice, stable sinusoidal like that. You often get lots of harmonics. So protection is the last major topic, and there's obviously there's various types of faults. Incipient fault takes a long time to develop, breakdown in insulation, and eventually they can become solid faults. For example, a cable underground has a protective coating, covering, and you could have a breakdown of that. Insulation breakdown. Transient faults don't damage the insulation permanently, tree branches, and permanent fault is when the insulation of a cable is broken down and you've got a problem. Permanent problem. Need for protection, obviously avoid electric shocks, electric burns, hard flash, fire. Overload, obviously you could have your house, you've connected something up which uses more current than the rating of the breaker, you get an overload. Obviously, overload protection is very important to prevent any faults. Over voltage, and again, you want to protect your system from over voltage, over current, motors, motor fault, and over current protection. Fuses, fusible links like that. Basically metal wire, and that breaks, burns out, and you protect your circuit. Fault in a piece of equipment, and overheating, possibly fire, and a fuse will protect you from damaging your equipment. Circuit breakers are typically what you see most of the time. You see it in your house, and you can obviously protect your electrical circuit. And obviously, when you walk into your house, you'll see a breaker tripped, and then you need to go and identify what it is. So then you open all the circuits in the house, disconnect everything, and then you gradually switch each circuit on. And then when the breaker trips, you know, my kettle or my geyser's element is gone, because that's what trips my breaker. And obviously, the very important thing with a protection engineer is that you need speed to deal with the problem quickly. And obviously, here's the fault occurring. That's when the fault is extinguished. And you'll see your trip coil energized there. Takes a bit of time for the relay to pick up, and the total fault clearing times on that time there to the actual fault extinguished. And that basically, protective relays are obviously important, and they can look at current voltage, magnitude, phase angle relationships, direction of power flow, and frequency. And obviously the idea is to disconnect your faulty system as quickly as possible, element, disconnect, and very important to operate quickly and effectively. So in essence, that will give you, these slides are available, gives you a quick rundown on the different parts of the power system, from the generation of the power, transmission, distribution, obviously usage of power, and all the areas with power usage, the harmonics. Obviously you have a transformer to step up or step down the voltages. So it's quite critical. So this hopefully will give you a quick run through on the different parts of the power system. And hopefully next year I can do this presentation in a more interactive way, but this hopefully just give you a quick rundown now.